Now we finally start solving some stuff. So let's consider A, where we are asked to find an expression for the adjustment coefficient R. Now, in fact, since we now know that we're just dealing with a Kremer-Lindbergh process where the net premium is given by C minus CR, and we know the distribution of the IID claim sizes to be exponential, there is actually a nice result that we can recall, which tells us that for a Kremer-Lindbergh model with exponentially distributed claims, we actually have a closed expression for the ruin probability, and it is given as the expected number of claims divided by the expected claim size, no, not the expected number of claims multiplied by the expected claim size, and then divided by the premium, multiplied by an expression that is exponentially decaying in the ruin probability by a factor r, where r is the adjustment coefficient. So what we are going to do in this exercise is we will calculate r, and then we will try to figure out how to maximize r in order to minimize this ruin probability here. And actually, since we know that the claim sizes are exponentially distributed, according to a very nice result in example 2.2 on Hansch-Schmidtly page 40, we actually have an expression for the adjustment coefficient in this case. So we actually know that the adjustment coefficient R should be given as theta divided by 1 minus A, which is also just the parameter in the exponential distribution for the claim sizes, and then minus the claims arrival rate divided by the premium. So that is a result that we know from example 2.2 and Hansch-Schmidtly. However, just for the sake of law and order, let's try to calculate an expression for the adjustment coefficient ourselves. And for that, let us recall that the adjustment coefficient is that number which solves this equation, which solves the equation that requires the cumulant generating function in minus r to be equal to 0, where the cumulant generating function is given as the logarithm of the moment generating function of the capital growth at time 1, where the capital growth x is defined as the total capital minus the initial capital. So if we had any other process than the Kremer-Lindbergh process, we will have to go in there and then calculate the moment generating function and so on and so on. But since we have the Kremer-Lindbergh process, we actually also have, so since the total capital is a Kremer-Lindbergh process, we have a result from lecture that tells us that then the cumulant generating function in minus r is equal to the claim arrival rate multiplied by the moment generating function of the claim size in this Kremer-Lindbergh process. And the moment generating function should be evaluated in r minus 1 as such. And then we have to subtract the premium in this Kremer-Lindbergh process, which is given as C minus CR, and then multiply by capital R. So this is something we know since the capital growth follows a Kremer-Lindbergh process. So actually we just need to solve an equation where we put this thing here equal to 0. And in order to do that, we have to figure out an expression for the moment generating function. So just recall that the moment generating function for an exponentially distributed random variable with some parameter xi, let's just write it out here. If we have some variable that is exponentially distributed with, what should I use? We actually have psi up there. So let's just say zeta, parameter zeta. Then the moment generating function of this evaluated in alpha is equal to the parameter divided by the parameter minus the argument of the moment generating function. So the moment generating function of these claim sizes here is given as the parameter, which is theta divided by 1 minus a, then divided by theta divided by 1 minus a, then minus the argument, which here is just equal to capital R. And if we multiply the entire fraction by 1 minus a, what we get is theta divided by theta minus R multiplied by 1 minus a. And in effect, when we subtract the 1, then we can see that nice things will happen. So let's just continue our calculations. Hence, we require that lambda multiplied by theta divided by theta minus R multiplied by 1 minus a. And then we take this and subtract the 1, which corresponds to subtracting theta plus R 1 minus a, just putting the entire thing into one fraction. And then we have to subtract the premium, the net premium earned by the insurance company, and multiply by the adjustment coefficient, and that must be equal to 0. Now we see that there are some things that cancel. First of all, this theta cancels with this theta, and then there is an R that's multiplied on this entire thing, and there's also an R that's multiplied on this entire thing. So if we just divide the entire equation by R, then these R's cancel, and what we then have is that lambda multiplied by 1 minus a shall be equal to c minus cr multiplied by theta minus r multiplied by 1 minus a. So essentially we just moved c minus cr to the other side and multiplied the denominator over as well. What we want to do is to isolate r in this expression. And how do we do that? Well, what we can see here, let's see, is that we can multiply the c minus cr into the parenthesis. Then what you get is c multiplied by theta, just say c minus cr multiplied by theta minus c minus cr multiplied by r1 minus a. Then we move the c minus cr theta to the other side. And we then have c minus cr multiplied by r multiplied by 1 minus a multiplied by a minus on the right hand side. We want to isolate r, so what we do is we shall have to divide by minus c minus cr multiplied by 1 minus a. And now we have an expression for r. But it's not a nice expression, so let us just rewrite things so that we can clean up a little bit. Cleaning up, we see that R should be equal to, well, let's just take the minus up here and flip these two terms. So the C minus CR comes first. And let's also just divide by C minus CR in all the terms. So what we have is that R is equal to theta minus lambda divided by C minus CR multiplied by 1 minus A divided by 1 minus A. And what you see is what we have arrived at now is actually the same expression that we got from the Schmidli example. And that's nice and all, but what we actually want is we want to get rid of the C minus CR and instead substitute it with an expression of A. And we had that from earlier when we wrote up our model. We had this expression up here. Let's just see if I can figure out how to copy this and move it down. La 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 la. Did that work? I think that worked. It's not pretty, but I think it worked. There we go. Okay, so let's just substitute this expression in there. What we have is theta minus lambda divided by lambda, so those two lambdas cancel out, and what we then have is divided by this entire thing multiplied by theta, so theta minus theta divided by psi minus psi r plus 1 minus a 1 plus psi r as such. And we also have to remember to multiply by the 1 minus a, and then we divide this entire thing by 1 minus a. And what does that give us? If we want to write that up in some nice manner, then we can see that there are thetas in both terms here. So we can take the theta outside of the fraction, and what we have in the first term of the fraction is 1 divided by 1 minus a. And in the second term of the fraction, what we have is 1 minus a divided by something, and then divided by 1 minus a. So the 1 minus a and the 1 minus a cancel, and we have 1, divided by psi minus psi r plus 1 minus a multiplied by 1 plus psi r. There we go. And now we have an expression for the adjustment coefficient, where, just for good measure, recall that we must still require for a to be strictly smaller than psi divided by psi r for the net profit condition to be fulfilled.